In class, at the end of class, before we went outside last time, we started talking about a position versus time graph for something that has a changing velocity. We used really super scientific terms to talk about the steepness of the slope, because remember, the slope of a position versus time graph tells you how fast something is going. So we use really super scientific terms to say here, where there is a shallow slope, things are going slowly, and here where there is a steep slope, maybe things are going a little bit quicker. So we used super scientific terms such as slow, fast, and medium to talk about the speeds of this object that appears to be changing its velocity. And then we said if we were to kind of redraw this or re-represent this on a velocity versus time graph, that start where things are slow, and you guys can't see what I'm pointing at right now, but I was pointing right there. Where things are slow, there is a no velocity or very little velocity, and then as time goes on, the velocity actually changes. And this is kind of where we left off before we went outside and started walking around, doing the walk-a-graph activity. But I wanted to define something, and these are our actual notes from earlier. I wanted to define the word changing velocity, because rather than saying changing velocity over and over again, we're just going to call that acceleration. And the acceleration is defined as the amount an object's velocity has changed in a given amount of time. Since velocity is a vector, acceleration also happens to be a vector. If we wanted to represent that mathematically, we could say that A, which is our math symbol for acceleration, acceleration is equal to, the triangle means change in, V represents velocity, and T represents time. So in math form, it says that acceleration is equal to the change in velocity over time, which is exactly what it says in word form also. Now, in your car, the accelerator pedal, the gas pedal, is the thing that we say that makes us go faster. But I would make the argument that by this definition, since acceleration is the amount that the object's velocity has changed in a given amount of time, so the amount of velocity change in an amount of time, that the brake pedal is also an accelerator pedal, just kind of an opposite accelerator pedal. One accelerator pedal makes you go faster, and one accelerator pedal makes you go slower. But according to this definition, the word decelerate doesn't necessarily exist. We're just talking about acceleration that makes you go faster, or acceleration that makes you go slower. Acceleration is the rate of velocity change. And here's what I mean by that. If you're traveling at an acceleration of 5 meters per second every second, and before we do that, we should probably run back and just quickly look at the units for acceleration, and my fault for not doing that earlier. And these units of meters per second seem a little weird. But if acceleration is defined as change in velocity over time, and velocity is measured in meters per second, and time is measured per second, then acceleration is literally how many meters per second you change every second. So if something is traveling with an acceleration of 5 meters per second for a time of 2 seconds, what this allows us to find out is that there will be a change in velocity of 10 meters per second over those 2 seconds. After 5 meters per second, if you started from rest, after 2 seconds, you're going 10 meters per second, and so on and so on. So just like velocity is the rate of position change, or how many meters per second you are traveling, acceleration is the rate of velocity change. And now would kind of be a good time to hit pause and work on, I think there's 3 plug-in sample problems on the front of that worksheet that goes along with this. So now would be a good time to pause me and work on those 3 things. And then when you're good to go, re-hit play. I won't go anywhere. So hit pause, do it. Do it, hit pause. You didn't hit pause yet. Hit pause. Cool. Good job with those problems. I'm going to clap it up for you guys. Good work. There's another way that we can kind of represent acceleration, and that comes from the definition of a straight line. So if we have something's motion represented by this velocity versus time graph, and a good spot to take notes for this is kind of at the bottom of that, the front page of that sheet. So if we have something represented by this velocity versus time graph, that thing looks like a straight line to me. Since this is a straight line, we can say the equation for a straight line, or y equals mx plus b, the y, whatever is on the y-axis, is equal to the slope of the line times whatever is on the x-axis plus the y-intercept. Well, for this particular line, and for this particular graph, this is a velocity versus time graph. So the stuff that's on the y-axis is the velocity. The slope of this line, or how quickly the velocity changes in a certain amount of time, we define that as being acceleration. And the stuff that's on the x-axis is the time. And the y-intercept here, let's call that the VO, or the original velocity, for this particular object that's moving, plus VO. Now, to do some rearranging, just so we do what everybody else in the world does when they're talking about this equation, we can write that as V equals VO plus AT. In word form, we can... So in other words, the final velocity, or the velocity at any given point, is equal to the initial velocity plus how much it changes over time. Since we're talking about motion in one direction, we can rewrite that using the symbol x, meaning the horizontal direction. You could also rewrite it using the symbol y, meaning the vertical direction, if you felt like it, but I don't. So the velocity at any given point, Vx, is equal to the original velocity in the x direction plus the acceleration times time. Now I'm going to put a box around this because this is a kinematics equation. This is an equation that's going to be very, very, very important, and we are going to be using this throughout the entire year. At this point, this would be a good time to do those 3 plug-in sample problems, starting first writing down the equation, plugging in numbers with units, and solving for the unknown that are on the back there. Try and sum this up in a big idea, and that is it. That's your homework. We came up with 2 equations, but they're really just the same thing. If we say that something is going a certain speed VO at the start, and then as it accelerates, it gets where it's going faster with a bigger speed, or slower, either way, since acceleration just means the change in velocity. This symbol right there, the triangle, means change. So acceleration means change in velocity over time. Well, change in anything is defined as final minus initial. So let's write that. Change in anything is defined as final minus initial. So let's write that as the final speed minus the initial speed, there's a cursor in the way, all divided by the time. Now I'm going to do a quick step of algebra and multiply both sides of the equation by t. T cancels with t. So a times t equals the velocity at the end minus the original velocity. Do another step of algebra and add VO to both sides. And we have that VO plus AT equals V, which is really the same exact equation that we just came up with. So they are just completely 2 forms Vx equals Vox plus AXT. They're really just two forms of the exact same equation, just with some algebraic manipulation going on there.